very happy to be here. I'm Doug Hatler. As we stated, I'm an environmental engineer, environmental scientist. I started in the hazardous waste and then moved into a lot of different roles, pharmaceutical industry, and now in the water and wastewater industry. Very pleased to be here. My colleague, Dr. Marc Deshusses, is our head of technology. Marc is also a tenured professor at Duke University in the Department of Civil and Environmental Engineering. Marc is the initial principal researcher that led to the research and development of this technology called SCWO we're going to present. It initially started with a grant from the Bill and Melinda Gates Foundation and progressed since then. He and his co-founder, Kobe Nagar, spun the company off created the company, in 2018. And we've licensed the technology from Duke University, and we're now commercializing what we call SCWO, SCWO being supercritical water oxidation. As part of our commercialization efforts and as part of our license and the work that originated from an initial grant from Bill and Melinda Gates Foundation, we have a program called Global Access. And Marc is heading up that initiative, and he's going to speak to that. We're also obviously going to introduce our company, and we're going to introduce the technology. But the global access is something that goes back to the very roots of creating this technology, and we're very excited to have this opportunity to let you all be aware of this program. And we hope that there's a fit here for technology and further discussion. The company itself, we consider ourselves to be bigger than just selling wastewater equipment or waste treatment equipment. We see ourselves as a social impact clean tech company. We're a virtual company, but we're based out of Durham, North Carolina in the USA. We are a corporation, and we are publicly traded right now on what they call the over-the-counter exchange. We are in the process of uplisting ourselves to the NASDAQ exchange later in this year. What we're doing is we're taking what the world views as waste, moving it through our technology, a kind of a blue box, and coming back to having clean water. I want to skip ahead. I'll come back to that slide, but we have a vision, and our vision is a world without waste. And you see that diagram is really what we mean by that is we're contributing to a circular economy where we can take the wastes that our society generates. We can take the waste that our society is generating, and we can break them down into the fundamental components of water, carbon dioxide, innocuous minerals that have potential recovery and reuse potential, and heat. We recapture energy as heat, and depending on the size of our units, it could be converted into electricity through an expander technology that would then put energy back into for reuse. So that's the idea behind what we call resource recovery. Our mission is to preserve a clean and healthy environment that sustains life. We recognize the sustainability development goals under the United Nations. The 7 nations achieve their own individual goals around those. And then we have values. We own, we transform, we trust, we learn, we impact, and we dare as a company. I'm going to go back here a second. Let me see. I got one slide I'm going to go back here a second. And, what we're trying to do with our global access program and around the world, but particularly in global access, is you can see, those two people are pouring essentially a 55-gallon drum of fecal matter. And in that particular country, this may be the norm for how it's disposed of. But that organic waste has 250 kilowatt per hours of power, which is a valuable resource. At this point, Marc, I'll let you comment because this takes you back to your roots, and then we'll skip ahead to that first slide that talks about the fundamental process underlying our technology.
Sure, and thank you. Thank you, everyone. Thank you, Mary, as well, to give us an opportunity to talk. Very pleased to be able to present this technology. So indeed, yes, this is when we started. 2013 is when the Gates Foundation was looking for ways to get rid of this problem. And we realized that there's significant energy embedded in that waste. And the challenge was, can we use that energy to turn this waste into something clean, recover resources, and avoid a lot of environmental and health problems. And the answer is that we came up with is this technology that we'll be talking about, and we're now commercializing the supercritical water oxidation, or SCWO. Greg, if you go 2 slides forwards, we have here. I'll tell you a little bit about the science, and then show you some of the features of our system, and then focus on global access and what it means. So this is the phase diagram of water, and probably, you know, everyone is familiar, of course, with, you know, water as a vapor, solid, or a liquid. But you should also know that when you compress the water above 220 atmosphere and heat it above 374 degrees C, hence the name of our company, the water gets supercritical. It is not a gas, it is not a liquid, but it has some amazing properties of both. Since oxygen is fully soluble, the organics are fully soluble in supercritical water. And so what that means is that, and there's also extremely rapid heat and mass transfer. So what that means, next slides, is that when you inject air into organic waste in a slurry that's been brought to supercritical, the following reaction is happening. It gets, all the organics get oxidized, recover clean water, can be reused. The carbonaceous materials are converted to CO2. Minerals fall out of solution, are readily available for reuse as a fertilizer. And then you recover the heat of reaction, because it's an oxidation, because of all that energy that I was showing earlier, is recovered and is generally re-injected into the process, because you want to make it a continuous process. And some of the surplus can be turned into electricity. So that's the gist of the SCWO reaction. And on the next slide is shown how we've engineered it to fit into a box that can then take any organic waste, fecal waste, pit latrine content, contaminated water, chemical waste, and others, and turn it into clean water and the elements. So if we follow here, if you follow the air, for instance, the ambient air gets compressed into a high pressure compressor, and then it passes through a heat exchanger, the economizer, which recovers the heat of reaction and heats up the air to high temperature. It's then mixed at the entrance of the reactor with the waste undergoing treatment, and that waste is slightly preheated for energy efficiency in another heat recovery system. In the reactor, the reaction that I was showing earlier occurs, and it happens in a few seconds. We're talking about 4 to 10 seconds for the reaction to occur, and it's extremely fast because of the conditions that I mentioned earlier. And then the heat is recovered. After the heat exchanger, we have a phase separation. This is where the permanent gases and some vapors are expanded in a heat recovery and energy recovery system, resulting in power used in the system, the vented gas, and distilled water quality. Here the water is condensed and is of very high quality. The other stream from the separator is the minerals that I was mentioning earlier, with some water as well, and that's fit for recovery. On the next slide, what you see is a picture of what we call the NIX-1 system. This is the original prototype that was built with funding from the Gates Foundation. We received funding to demonstrate this technology, to de-risk it, to bring it to a stage that it can be commercialized. Receive about $5 million from the Gates Foundation, and about $1 million from other agencies. And what the characteristics of this system is that it's very compact. This is a 20-foot container, and this can treat the waste of 1,000 people, 1 ton a day, 1 wet ton per day. It's a continuous process, and it produces clean water. We'll show you some pictures or videos later. There's no odor, you know, with water, wastewater, fecal, sludge. Odor is a big concern. There's no odor, so you can place a unit like that in a neighborhood. It also destroys every organic chemicals. There's no organics that has not been destroyed, that we fed to the system that hasn't been destroyed. And Mary mentioned PFAS, PCBs, emerging contaminants, they all get destroyed and mineralized. You can do this with multiple waste mixed together, fecal waste plus chemical waste. Everything is disinfected because of the heat. And you can do it with waste without dewatering, without drying. Now, there are certain requirements as to the concentration of organic, and I'll get back to that. But the beauty of this process is it's relatively simple. It produces very clean effluent, and you don't need dewatering. On the next slides, you see more pictures of the system, how it is in the interior. It's all industrial equipment. And some further attributes that the units are small, and you can locate them on the premise, embed them at the source. By the way, my background is inside the unit as well. The pictures you see here is before the thermal installation was placed. And very relevant, I think, for the audience today is to realize that, we recover and we can reuse water. We can treat fecal waste as we mentioned, but recover energy from it, recover nutrients. I think in today's context, I know India is going through a huge revolution where initiated by the Swachh Bharat mission, but also some of the stringent requirements placed on wastewater treatment. There's huge demand for toilets, there's huge demand for small scale systems, and we think this solution has a role to play. And so in decentralized units. The process is very scalable, so it can fit multiple needs. And it's very energy efficient. And as we started talking about sustainability, Doug mentioned the sustainable goals. Is really, I think, very relevant to that. Next slide, please.
It's very.
And on the video, what we'll show you is the ability of the unit to treat a variety of waste. As I mentioned, we've done a lot of work on biosolids and fecal sludge, but this particular video is showing that we are adding microplastics just to show that we can treat ground plastics. We can treat waste oil. We can treat yes, and that's gist of this video.
Can everyone see the?
Yeah, we can see it. Thumbs up.
I'm going to take away the music in the background, and so what we have is we have biosolids at the bottom, and then we're adding plastic. The plastic is not a feedstock. It's not necessary. It's just adding to the demonstration of a blended waste of biosolids, wastewater, think of those as being microplastics. So we're demonstrating that we can treat plastics, and then we're going to add some foods, fats, oils, and greases. This is why we have a cholesterol treatment medications in the world. But so that's going to go into the now this is at the NICS-1. This is at Duke University. That's a Duke University pilot system that 374 Water uses under a sponsored research agreement for treatability. But what they're doing here is making that uniform, consistent feedstock that's about 12 to 15% total solids. They're pouring it now into a feed hopper where it will go from a low pressure pump into a high pressure piston displacement pump, which will then move it through the reactor. That's the actual material that's going into the system itself. And what you're going to see is there's the NICS-1, the blue container. It's a 20-foot cargo container. And voila, that's what comes out, minus the gases that are coming out, but that's it. All those solids, 99.9 or higher percent removal of volatile solids. COD reduction goes from 160,000 parts per million or 200,000 parts per million down to about 118 parts per million. Any organics that might be in there, microplastics, drugs, if you did have PFAS, anything else that's in there is generally going to be mineralized to CO2 and H2O, and then any inorganics there are going to be oxidized to the lowest oxidation state of whatever else is in there. They may form precipitates with other compounds. They may just be in an ionic state, but that's it. So that's the idea, behind our solution. So now what I'm going to do is I'm going to go back to the slide presentation. And I think at this point, why don't we stop, Marc, and just see, let me see where we are next. Let's stop and take a question. If there's any questions about the technology.
Get to the next slide, next two slides, and then we can take questions.
Great.
No, get on the slide that shows the minerals right after the video.
Is this
Yes.
what you want to
So
show?
here's more. Just again showing the diversity of things that go in and how clean what is what comes out. And you see a picture of the minerals, and those contain all the phosphorus. Also, just on the next slide, you have some attributes of the water effluent. Just again, we're coming in with very high concentrations. That's the feature that's required for energy efficiency, either as COD or as a solid content. Very high nitrogen, phosphorus, and then what comes out is the water, very clean. And maybe indeed, as Doug said, before we get into telling you about our global access program and our plans, let's take questions on the tech.
Yeah, so just we'll close out the tech and open it up. So we right now, what you'll see over there in the dotted line is the NICS 1 unit, which is the pilot system that sits at Duke University. We at 374 Water are currently in the process of manufacturing 2 NICS 6 units. Those are 6 wet tons per day, approximately 6,000 human individuals, population. The first unit is going to Orange County Sanitation District in Fountain Valley, California for a demonstration project. They will be treating primary sludge mixed with concentrated thickened sludge. We will be putting that combined material, which has about a 4 to 7% total solids content, through a dewatering unit where we will put it through a screw press, and then we will thicken it up to about 12 to 15%. And then it'll go through the NICS 6 system, where we will then treat it with the SCWO process. And what will come out will be what we talked about earlier. We'll have a water stream that's distilled water. Some of that distilled water will be reused in cooling and providing water into some of the equipment. And then what's left will be mixed with the water and mineral solution that comes out of the reactor itself. And we'll be sampling the minerals to see what the mineral content is to determine if we can valorize the minerals, as Marc said, as a fertilizer. Then we are at the drawing boards right now on our NICS 30 unit, which is a 5 times scale up. So that's 30 wet tons per day. That would correspond to the solids from about an 8 to 10 million gallon per day plant. And then there's a zero cutoff on the NICS, that should be a NICS 200, which is a 200 wet tons per day, which would take you up to about a 30 million gallon per day wastewater treatment plant, or the solids from the equivalent. So that is the technology, that is, and those are the commercial offerings. In terms of, people are going to ask about cost, which we can get to a little bit later, but we will be looking at doing a number of different ways to offer this through purchase, which can be a cash purchase or it can be financed. We're looking at offering leasing options, and we're also looking at an as-a-service option where we can either do it ourselves or team up with a local service provider. The unit shows up, gets connected and operates, and it's run by a contract operations or as a service group, and the cost basis is on capacity and throughput of what the treated waste itself. So with that, again, we promised to pause. I will pause, and let's open it up for questions about the tech and the commercial offering. And then what we're going to follow up with, we want to leave about 5 to 8 minutes, maybe 10 minutes, or 5 to 7 minutes if we can, for Marc to just describe the global access program to see how it resonates with you all and some of the things that are going on in India. And then we'd like to hear about the specific needs in India that might be applicable to a technology